Yeah, thank you very much for the opportunity to be here. First time after the pandemic, it's great to be back to India after a while. The program is about condensed matter meeting information. I will be absolutely spot on. The information side in my talk will be represented by industrial grade quantum computers, superconducting quantum computers, and the condensed matter side by the physics of many-body localization and somewhat more specifically quantum chaos. Now, contrary to what you might anticipate, I will not talk about simulating MBL, many-body localization on computers, but the other way around. I want to discuss with you how principles of condensed matter physics, many-body localization, and quantum chaos affect current-date quantum hardware and bring some of it, we believe, dangerously close to a state of nervous breakdown due to principles of chaos. This will be the story. Let's start slowly by recalling that at this point there are several platforms of qubits out there: spin qubits, Rydberg qubits, ion qubits, and superconducting qubits. And among them, the transmon superconducting qubit plays a distinguished role in as much as, number one, our most powerful computing platforms we have, give or take 100 halfway reliable qubits, are realized in terms of transmon qubits. And second, the big players are invested in this particular platform, notably Microsoft and, excuse me, not Microsoft, but Google and IBM. They are fully invested into the transmon. Microsoft or something else. And that means that there is a lot of money in this game. Yeah? Good. So let's take a look at the transmon as such. This will be our main protagonist in this talk. It's a superconducting qubit. And as such, essentially a parallel shunt between the Josephson junction and a capacitor. And you can describe this quantum mechanically by the simple Hamiltonian here. So there's a capacitive term, there's a charging operator. And here we have cosine phi, the conjugate phase of the charge operator, representing the superconducting junction. And what makes now the transmon somewhat different from other superconducting qubits is that this Josephson energy here is by far the largest energy scale in the game, for reasons that I don't want to discuss. But this is the transmon. Think of it as a simple quantum mechanical Hamiltonian. As such, it has a discrete spectrum. And the lowest two levels here, they are the qubit. They represent the qubit state. Yeah? So that's the transmon. Now, transmon physics will play quite some role in the following naturally, and I want to look at it from different perspectives. One I mentioned already, it's the Hamiltonian as such, but you can represent it in somewhat different ways. One of them being, if you want, a low energy approximation, which is appropriate to describing this physics around here. And what you essentially do is you Taylor expand the cosine. So to leading order, you then get an harmonic oscillator, quadratic expansion. To actually capture the full physics, we need to get a little higher, up to quartic order. So we have a mildly nonlinear oscillator. That is our system. Another perspective that will be useful is to think about it as a classical system. You simply switch off H bar, all your operators become functions. And what you then have is this Hamiltonian here, or this Hamilton function, which is the Hamilton of a mathematical pendulum. Yeah, you have seen this in your first year. Pendulum Hamiltonian looks like this. It's a bosonic creation operator. Think of this, if you neglect this guy, this is the standard harmonic oscillator representation in terms of creation and annihilation operators of a linear oscillator. Huh? No, in this harmonic oscillator approximation, you would get an equidistant sequence of levels, and the nonlinearity gives you this. And you need it, thanks for that. You need, because a qubit wouldn't function with an equidistant sequence, you would get resonant processes. Okay, so this is our player, yeah, the transmon. Now, I mentioned that Google and IBM are invested into this, but they follow subtly different strategies in their approach of building superconducting quantum computers with this. And they are actually interesting. So what does Google do? Google is extremely careful with its hardware. So they meticulously try to protect their transmons against external influences by mechanisms which I don't have the time to discuss. But the net effect is that Google still is hovering around 53 or maybe 70 qubits after 4 years or so. Yeah? In 2019, they came up with their Sycamore chip. They're still playing with qubit platforms of this size. And what they do is they do amazing experiments with that. For example, I mean, after this morning's talk, toric code anion braiding was a recent experiment. I mean, super nice experiments. And that's what Google essentially does at this point. Now, compared to IBM, IBM is much more aggressive in scaling up qubit numbers. So what they do is they publish every once in a while an updated development chart, and they are on a steeper track, I think, towards actually selling their machines or maybe selling cloud computing services. And this is here the current IBM roadmap. You see here different processors, 27 qubits and 65. We are currently at Osprey. For some reason, they like to name their processors after birds. So this is where we are here, Osprey. A Condor is to come later this year, and then there's Flamingo. Someone, anybody knows what a kookaburra is? Yeah. So here it is. So it's not quite that guy, but the Australian version of it. Yeah, it's an Australian kingfisher. It's called kookaburra, but for me this is the one. Anyway, so this is IBM. There is another nice thing about IBM, or not another, but a nice thing. They are extremely forward with publishing data on their qubits. So you find all kinds of details on hardware, frequencies, everything. You find it on the web, which was good for us because I show you lots of simulations in the following. They were all done for the real thing. I mean, for actual IBM processors. And this was very useful. While Google keeps its secrets closer to its chest. Yeah. Okay, so this is roughly what these two are doing. And now I come to the main subject I want to discuss with you, influences of chaos in this game. And I will begin by looking at the transmon as a purely classical system, for reasons that will become clear. Then we go quantum. And in the third part, we look at really realistic current date processor designs. And maybe if I have time, I touch a little bit upon dynamical gate operations. Yeah. So let's do the first thing we have to do. If you want to build a computer, we take not one transmon, but several of them. And that gives you this kind of array structure. So we have a bunch of transmon here, 4 of them, each having one of these Hamiltonians, and then they are coupled by what actually is a capacitive coupling. So you do a momentum variable coupling. What I would like to keep you an eye on is this scale here. So the Josephson energy is the largest energy scale by far. And what's very important is there is fluctuations from transmon to transmon. You have a slightly different EJ. Now you might say, oh yeah, of course, because I'm building something, so there will be material fluctuation, but that's not the point. The point is that they have to be different. And IBM actually, and Google, they put intentional fluctuations, random fluctuations there. So they disorder their system intentionally. Why? Because if these scales were all the same, then you would have a system of perfectly resonantly coupled nonlinear pendula. And that is a massively chaotic system, both classically and quantum mechanically. So you would die a sudden death due to chaos. Yeah? So making this different, detuning these guys is a way to protect you against chaos. And that will be important in the following. I mean, okay, what I did here is I just, I meant to indicate a few qubit occupations. There's no difference. It was just, I mean, this, oh, sorry. This would be one qubit state 1, 0, 1, and here's a doubly excited. I mean, I just plotted the representative state. So there are these fluctuations, and I mentioned this scale. Now, there is a little fine print to consider, a hierarchy of energy scales. Let's not worry too much about that. What I should want you to remember, perhaps if you can, is the following. This guy is by far the largest scale. Then comes EC, and then comes the disorder. So the disorder is, and the disorder in particular is much stronger than the coupling. Yeah? So we have much stronger variations than the coupling itself. People knowing about MBL may already anticipate that this is going into somewhat many-body localization direction. Good, now let's first look at the system in the classical limit. This classical physics, so we forget about H bar, we have a bunch of pendula, and I think of them initialized at some energies, and energies to watch out for are the classical energies that correspond to the quantum levels once you put H bar on, and they are naturally relatively low energies. Yeah? So we have a bunch of mathematical pendula coupled, And let's start, before starting, remember this EJ was disordered. So each of them experiences a slightly different gravitational potential due to these fluctuations. Yeah? This is our system. And let's now look at this in the simplest possible case, just two transmons coupled, classical. And what I want to do now is just as an exercise, I want to seek for indications of chaos. You know that coupled nonlinear pendula, I mean, they are desktop toys, are paradigms of chaos. So we can simply simulate them, initialize them at a certain distortion angle and see what we get. And what we plot here is so-called Poincaré sections. You don't know what a Poincaré section is. A circle or a closed trajectory means you are integrable. Everything is fine. Once you see the snow, you are in a danger zone. This is chaotic dynamics. And what we see is that as we increase this distortion, there is really beautiful manifestations of chaos. I mean, in all glory. I mean, you have here this section, and then if you look closer, you have principles of self-similarity. So there's people who know chaos, KAM tori, satellite tori. I mean, it's beautifully chaotic. Is this relevant in any way to quantum computing? The answer is clear-cut no. Why? Because in order to actually realize this chaotic dynamics, you have to go to distortion energies which are really high, much higher than the qubit energies. If you really stay down there for what is relevant for quantum computing, you are nicely integral. So you could say everything is nice and fine, project closed, let's do something else. But before doing that, yeah, sure.
All your explanation will be in one dimension, or doesn't matter?
No, 2 dimensions. I come to arrays here. Yeah, it's coming. A number in phase, yes. These are number in phase, or momentum and coordinate, if you want. So you have 2 transmons. Each has a coordinate. This is phi1, and here's phi2. And then they have both conjugate momenta. The momenta we call n instead of p because it's pendulum. Was there another question? No? Okay. I'm rushing a bit because I have only these 30 minutes. So this was a little longer. But anyway, no, it's first. So let's take 10. You might say stupid exercise. I mean, why? We have already seen that chaos is not relevant. But here's the argument why it might still be. Suppose you have these 10. Energy is only globally conserved, not locally. So each of them has a certain energy. On average, they are low. But what might happen is that these guys here conspire to push all their energy in a fluctuation to maybe that transmon. And then this single transmon will be in a somewhat higher excited state, and you might enter into some dangerous zone. Yeah? It's a feeble hope. When we did this, we thought probably not. But still, you can give it a shot and see what happens for 10 transmons instead of 2. And what we do now, I mean, we can no longer do Poincaré sections. This visualization works only for 4 degrees of freedom. What we do instead is we compute Lyapunov exponents. That is, we initialize trajectories in this 20-dimensional phase space, and we see to what degree they exponentially diverge. If they diverge exponentially, we have a divergence rate. It's called the maximal Lyapunov exponent, and that will be an indication of chaos. What you see here is a color chart. Color chart as a function of coupling and Josephson energy of this Lyapunov exponents. And you see that down here, no coupling, they are 0 essentially, but then you actually get some. You get some exponential divergence. And let's now see what it means for a real single transmon. And for that purpose, these insets here show you the following. For a transmon realized here, very low coupling, small Josephson energy, we initialize a trajectory such that it's 1 qubit energy is at level 1 and the other one at 0. And you see, these are actually these 2 here, and you see that they basically stay there. So these qubit energies, they stay where they are and down here. So you would say this is a classical cartoon of a good quantum storage. Yep, the 1 qubit remains in this energy, the other one remains here. However, if you go here, this happens. You get massive fluctuations. And you see in particular that this energy here fluctuates so strongly that the energy oscillates between 0 and 1. And quantum mechanically, you would interpret this as a scrambling of information. So your quantum storage is compromised here. Yeah? Yeah? That's the coupling between qubits and dimensionless units. So here's a somewhat more scientific way of representing this. If you plot this data as a function of t square root of Ej, it's a scaling variable, then these Lyapunov exponents collapse to a single curve. And what I want to convince you of later is that Lyapunov exponents larger than 0.02 are a danger for a quantum computer. And you realize that, you actually cross into this region when you scale up the system a little bit. And this is the first indication that something might be dangerous. Before discussing this further, the consequences, let's now quantize the story. Now we look at the very same array, but quantum. So same story, but now we have quantum oscillators, and now our levels here are real levels. Yeah. So these are, and this would be 0, occupation 1. I will discuss in a sec that higher excited levels, 2, 3, 4, are also important. Although from an information perspective, you would like to stay down here, the higher ones are still relevant. So the first thing I want to do now is let's take a look before connecting to the classical story. Yeah? Let's take a look at the many-body spectrum. So what you see here is a many-body spectrum as a function of coupling, and then you get here some energy scales, these stripy patterns. It doesn't mean much to you. What the meaning is that each of these multiplets here is a multiplet of a given total excitation number of your transmon. So this would be, say, the 5 excitation threshold. This could be that out of your 5 transmons, 5 are in a 1 state, or maybe 1 is in a 2 state, and 3 are in a 1 state, and maybe 4 and 1. Of interest for us in quantum computing are these guys. So this is the coarsest way in which a spectrum is organized of the many-body spectrum of the array. Now let's zoom in. So we go to a finer resolution and see now actual many-body levels. I mean, a jungle of many-body levels. Nobody can make sense of that. So we zoom in further. And now you see here this jungle. I mean, actually, there are some patterns emerging. The red guys here, and this is not a cartoon, this is actually a real thing. The red guys are computational states. All the others have higher excited states in them. Yeah? You see that the computational states we want to work with are energetically degenerate to states we don't like. And if you now zoom in further still and increase the coupling, you see this here, you see levels breaking up. And that here is now fully exposed quantum chaos. So you have all these avoided crossings, which are a signature of quantum chaotic systems. And what it means is that your information is deeply compromised. You know, I mean, this level here, which in principle should be a computational state, is hybridized strongly with a non-computational one. So here you are basically dead. Yeah. Yeah. Come again? Yeah. Yep.
How do you know that not continuing the other way?
Yeah. Very good. Yeah, thank you. It's an excellent question. It's actually a headache to do this. You compute fidelities. You compute not just the levels, but also the matrix elements of states. So if you think about a Landau-Zener process with just 2 levels, you can then say that this guy here is almost aligned with this one, but these are almost perpendicular. Very good question. It actually, this is how it's done. So how do we understand this kind of spectrum? Now I'm getting more to this many-body perspective. So here's our Hamiltonian again. What we can do is we apply now this low energy approximation, which I mentioned earlier. So we go to an oscillator representation. What we have here is a quartic Hamiltonian of individual transmons weakly coupled. And this here is a bosonic Hamiltonian. More precisely, it's a model Hamiltonian for the attractive Bose-Hubbard model. Right? It is an attractive Bose-Hubbard model, and as such a model Hamiltonian for MBL, for many-body localization. Many-body localization is about a fight between these couplings that want to spread states and the disorder, which is sitting here, that wants to keep them localized. Now, if you look at this Hamiltonian again, I mean, or have this picture in mind, and as a function of coupling, you want to have more and more hybridization. Yeah? If you're here, you are deeply localized. There is no coupling. Qubits stay where they are. Here, they are hybridized. And you really see this in the structure of the spectrum. Here you have lots of crossings. Levels are independent. They are localized on qubit states. This is good for storage. I mean, storage would love this. Here, you are totally chaotic. You have lots of avoided crossings. I mean, states are ergodically extended. This is an extended phase. This is a Fock space or many-body localized phase. Unfortunately, you want to be here in this twilight zone. You cannot be here because you cannot do with a quantum computer where qubits don't talk to each other. You are perfectly isolated. It would be a good storage, but useless for everything else. Here you have in a meltdown. So IBM engineers really try hard to be right here in this dangerous twilight zone. Yeah? And we can now make this more quantitative by computing many-body spectral statistics. And I mean, in view of the time, I cut this a little short. So, but what you find is indeed, if you look at the level statistics, the statistics of the spectra, you find beautifully exposed Poisson statistics here, and as beautifully exposed Wigner-Dyson statistics here, and some junk in the middle, where you want to be. And that happens at some coupling of 30 megahertz or so. Current date mega couplings are hovering around here for reasons I'll explain in a second. So this was our indication that, that there is actually this chaos is real in these devices, in the quantum device. We can now look where experiment is. I mean, actual experiments these days, I mentioned it, are performed here. Earlier experiments, I mean, earlier quantum hardware was here. You can say, yeah, it doesn't look too bad. The chaotic zone, where you are close to a Wigner-Dyson distribution, is relatively far from the experimental reality. But let's now be a little bit more careful and look at another indication of chaos, which is actually closer to what we want to do. We want to work with states. Yeah? States are what we use to store information in. And what we can probe is how extended states are in Fock space. In this, I mean, what I mean by that, you think of this here as a symbolic basis of your super high dimensional Fock space basis. The given qubit, which would be perfectly stored, would be concentrated on one of these states. A totally useless state would be globally extended, and real states are somewhere in between. In terms of this indicator here, IBM wants to work in a region close to 0.8. If they go below 0.8, they are in trouble. Now, what we can do for our same transmon array is compute these inverse participation ratios. And you see that we are now squeezed down to this corner here. If you are up here, your states are already too extended. You don't know if you're, I mean, you can't associate them clearly to given qubit states anymore. So we have to be here and hover around in this corner. Now, there comes a final, so this is telling us that from the perspective of wave functions, the situation is worse, yeah, than what you get from level statistics. Then there is a much more refined diagnostics, which I will not discuss here, where you really look into the internal anatomy of quantum states. And the keyword here is Hadamard-Walsh transform. And I skipped this here, but let me just mention that in the end of the day, it turns out that we have progressively more refined indicators telling us that if you want to be safe, if you want to operate your quantum computer safely, you have to be here down to couplings which are really very, very low, of 1 or 2 megahertz. Otherwise, you are in trouble. Trouble would mean that you apply 2 Hadamard gates and you don't get 1 or something like that. Yeah. So that is the toy problem of a 10 transmon array, which was modeled after IBM parameters, but is arguably not very realistic. Actual chips are 2-dimensional. So on. And let me now quickly touch up on actual realistic designs and see if this is relevant in any way. And the first thing to notice is that actual chips are 2-dimensional. And second, IBM does invests an enormous effort into designing combinations of regular and random frequency patterns to minimize the effects of this chaos on the MBL phase. And finally, actual chips are large by now. Yeah, they are in the hundreds of qubits. So how do we do this? That we have the first thing we did is we repeated our analysis for actual 2-dimensional IBM layouts. By that I mean for those who have heard, IBM has a geometry in their chips they call heavy hexagon design, where you have ancilla qubits and real qubits, and then there is this color coding represents intricately designed frequency patterns. And what they then do is they manage IB inverse participation ratios here. It's this sweet spot. I mean, there's a delicate engineering involved, and they fine-tune their system such that they are at this IPR maximum here. Yeah? here you are too disordered, and here you are too clean. So you are somewhere in the middle. Well, I mean, we have looked at all these Fock spaces and 5 minutes? Oh, 0 minutes.
5 minutes.
It says 0. It means 5. It's not just I equals 1, but 0 equals 5. Very good.
5 equals 0.
5 equals 0. Okay, so I mean, we saw that. I mean, basically, all what I said carries over. Only that in the real designs we have much more fine tuning going on and getting a lot more difficult, but delicate. But I don't have the time to discuss this properly. What I would like to discuss is finite size. I mean, so far, what we can do on our classical computers is we can do no more than 10 transpons, because we have to simulate the entire Hilbert space, including all these high-lying states. It's enormously expensive. But then, I mean, actual chips are large. I mean, Condor will be here the whole thing. I mean, so much larger. And the question is how to deal with that. How can we say anything about large systems? Does it get worse or better? Yeah? And the way to go is the following, or that's at least what we could come up with. For the systems that we could control, we computed these inverse participation ratios as a quantum signature of chaos or MBL. And at the same time, for the same systems, we switched off H bar and computed Lyapunov exponents. And you see here that for different values of disorder and coupling, there is a quite good matching between these color codes, meaning that's quantum to classical correspondence. Whenever you have classical chaos, you have quantum chaos and vice versa. So there's a perfect correspondence between IPRs and Lyapunovs. If you trust this and look at this with a loving eye, then you would say, now, yeah, maybe the Lyapunovs are already sufficient to tell you whether a processor is in danger or not. And if you accept that for a moment, then you can utilize the fact that Lyapunovs you can easily compute for 4,000 qubits for a realistic design. So solving a first order differential equation, that's much easier than doing quantum simulation. And that's what we did. I mean, we computed Lyapunov exponents for realistic processor sizes. And what you see here is that it's getting mildly worse. So if you go to larger processors, the Lyapunov exponents grow. I mean, you definitely don't want to be here. You have to be down here. But then in the thermodynamic limit, Lyapunov exponents are predicted to saturate. Lyapunovs are a local quantity. So larger processors are a little worse, but eventually they will saturate at some value. This is, so can take it as bad news or good news. It definitely doesn't get better. So let me more or less conclude with two remarks. Where's Google in all this? Google is totally safe. What Google does is Google off operation, they use so-called tunable couplers to isolate their transpons. If they don't do anything with the transpond, they shut it off. So they have very strong intentionally introduced blockades, and for that reason, everything is green. And so I think this is one of the principal reasons why they use much more expensive hardware, meaning more transmons, which act as decoupling transmons, more expensive, but also more reliable. That's one statement here. And finally, I want to say a few words, just a few on dynamics. I mean, so far I've just touched upon only computers for storing, but eventually you want to do something with it. Doing means you want to perform gate operations. Gate operations can be single qubits or 2-qubit entangling gates. What people do is, quantum mechanically, a gate is a unitary operation performed on 2 transpons, sometimes 3 with an intermediate transpond. So you cook up a unitary that does what you want to do, and people do this by methods of quantum optimal control. It is like for a given hardware, a given intended output, they optimize for the best use that do the job. These U's here are actually quite complicated objects. I mean, let me just flash some of these dynamics in a certain representation. I mean, so this here, for example, is an entangling gate. It's relatively complicated dynamics. What I mean by complicated is the following. Let me just gloss over this here. This kind of piece of art, that's what I mean by complicated. Let me go back here for a moment. What you see here is, as a function of time, the instantaneous eigenlevels of one of these unitary guys in a Fock space of dimension about 150. if you have 3 transmons, you don't get away with the low-lying states. About half of the spectral weight is sitting in these highly excited states on operation. So you actually optimize your protocol through a crazy jungle of many body states by brute computational power. And if you look closer, and these are the first 3 nanoseconds. If you look closer, then you see here, there's a crossings of these instantaneous levels, but then here, there is this forest here, where levels break up and you have lots of avoided crossings. If you do now level statistics of these unitaries here, you get something in between Wigner-Dyson and chaos is total mess. But one thing to remember here is that these guys are, engineered protocols maneuvering through a chaotic spectrum dynamically. And the way they can make their way through, in spite of chaos being present, is because this is a finite dimensional Hilbert space. So computing power just does the trick. Yeah? If this was infinite dimensional, you would say it's chaotic, no way to do anything controlled. So gate operations too are in a somewhat tricky situation. And if you look really close into these levels, patterns, you see again all these avoided crossings, there is chaotic dynamics going on. And what it amounts to is that fast gates, if you want to be really fast, you want to have fast gates, yeah, I'm not, are extremely sensitive to tiny material deviations. Yeah? If you change materials a little bit, at some parameter in your Hamiltonian, change it, you get a large error. And that's again something one has to consider in these systems. Yeah, and then on that basis, that's basically the story in a nutshell. I would have needed a bit more time to discuss this properly. But it's a Faustian design principle here. Yeah, that's why we invite disorder into the device. We have to do it, and now we have to live with the consequences. That's I think a message that one may have in mind in this business. Thank you. Yeah.
Okay, let's thank Alex.